看来大家都放假去了。It's OK 啊，所以呢，呀，等一下我再讲那个考试的事情啊，考试的事情。那其实今天来之前有一些想法哈，想跟大家分享，不过大家都不来了，所以就跟你们分享哈。那个to local students, so it's in Chinese, it's okay. Well, I'll tell you what's in my mind. 呀，这个课呢是我们这个怎么说？我们这个课呢是英文的这个物理哈，英文的这个物理的这个学程 ，OK。那最近听到几个同学，我因为不是很清楚，没有跟大家有机会仔细的这个了解哈，所以我并不清楚大家对用英文上课接受的程度怎么样啊，接受的程度怎么样 ？OK， 但我想并不是很容易啦。I'm telling them that it's difficult to learn both physics and English at the same time. 啊，所以呢，physics is a difficult subject, you know, right? Yeah. So 物理是一个很难的一个科目哈，所以呢，比较起其他 compared to other 其他的这个 like earth science or something else, it's much more difficult, more abstract, more mathematical, okay, more rigorous in a sense. Okay, I hope it's more useful to your future later. So 因此呢，你要学英文，如果你不是从小在 English 那个的 environment, it's really difficult to really learn English fast. You really need a long-term immersion. 你要一个长时间的泡在那个 immerse yourself in the English environment to really speak and listen and understand English. I hope you agree with me. Okay, so 对这个本地的同学来讲，好 ，it's very difficult. You are facing two challenges at the same time. 一下子你又要学物理啊，你才大一嘛，啊，一下你又要整个的这个 immerse 在一个英文的环境里面。我都在想，我讲的笑话，你不知道知不知道我那些字是什么意思 ？OK， 好 ，Yeah, but it doesn't matter. 好 ，Let me get to my point. My point is learning English, speaking it. And listening is a long-term process, but physics is your short-term priority. I hope you understand this message. 学英文是一个长程的一个努力啦，但是呢，物理才是你的一个进程的 priority。中文怎么讲？优先的一个顺序。OK， 所以 you can take 4 years, 5 years, and You will speak English if you do have the determination. You're sooner or later learn English. When I went to the United States 30 years ago, I don't have that much English. Much poorer than you do at this moment. Okay, so yeah, but if you immerse that environment, you have to speak every day, and you are forced to talk to your advisor in English. You will learn English. So it needs an environment. It needs an environment. Okay. So we try to create a semi-environment in this 学程, this international course. However, it couldn't be possible for you to really become a fluent English speaker. It's not that fast. It's just not that fast. There are so many words you won't be able to absorb so soon. You are not in that culture, so it takes time. But sooner or later, you will be there. However, I have to emphasize, you only have 4 years. Actually, you have 2 years to familiarize yourself with physics. So physics is the more important priority. Okay, that's why I almost write all our material in PowerPoints. That's the point. If you don't understand me in class in English, then you could at least go home and study the PowerPoints. Got my point? Okay. So, for example, if you only understand 1/2 of my English speaking, maybe it's not your fault. It probably is mine. It probably is my accent. Okay, I have a very poor accent, so you don't understand me. But even now, actually, I don't understand Indians Indian. It's not a problem of them. It's me. I cannot understand Indians' accent. They have very, very strong accent, so I couldn't follow them, even now. Okay, so it probably is my problem. 好，或许是我的问题，我讲的英文就是不够好，所以你可能只能学到一半。好，上课的时候。But everything is on the PowerPoints. Okay, so that's my point. You have to go back home and study and study and study because that's your future. English may be your future, but it won't be so fast. But physics will pile on. The difficulty of physics will pile on very soon. 它会一个马上就出现了。See my point? If you 今天呢，我们要讨论的是那个 complex number 的一个系统的解法。你这个没有学会，你明年的力学就完蛋啦。力学没有学会，波方程式没有学会，你再来电磁学就完蛋了，你再来的近代物理就完蛋了。So the difficulty of physics will pile on. 就是你这一个 this part, if you didn't understand this topic well, then it will stop you from learning new things. Okay, so physics is really priority. Okay, so yeah, that's my point. If you don't understand my English in class, okay, maybe half, then study the PowerPoints. Almost all the materials, important materials, are in the PowerPoints. Okay, at least you understand. And a lot of my PowerPoints is in Chinese. Okay, so you can at least, I hope you can at least understand the physics. Again, physics is your priority at the moment instead of English. English is long term. As long as you have a determination to immerse yourself, you sooner or later will learn it. But physics, well, not so easy. 相较之下，物理比较难学啦。我的意思是，相较之下，物理比较难学。你们如果没有趁你刚进来的时候把物理学好的话，你的这个困难度会一直不断的累积下去。很快呢，你就发现奇怪，物理怎么这么难？这本来就蛮难的嘛。You look at these notations, it's for a non-professional, it's almost like something that not intelligible, right? But you are chosen, not chosen, but you choose to be a physics professional. So it's your chance to get yourself acquainted with these very powerful, actually very powerful, even though it looks non-intelligible, but it's really powerful to understand nature and advance your career. Okay, 它同时可以让你了解自然，对你未来的生涯也非常有帮助。如果你要去台积电，你要去这个 high technology company 的话 ，this is the things you are going to use, really. Okay, so yeah, physics, and physics. Okay, although this course is in English, but physics is priority. Okay, so raise your question. If you have anything you don't understand, again, it may not be your fault, it may be mine. So I didn't clarify things enough. Sometimes I assume you understand something. For example, today I'm going to talk about complex number. 好，今天我会讲复数。local student 都知道复数是什么，高中都学过。Probably you don't do quite well, so you probably need to study a little bit more about the complex analysis. I'll tell you which material to go to. But it's so powerful and so important. You will appear again and again in your future study in physics department. Okay. Any question about this? And today we are going, because it is one day before the spring break, everybody's gone, so I don't want to keep you here for so long. But I want to really focus on one subject. And it is important. It is very, very important, very, very useful. Okay, it is called a systematic way to solve the linear ODE. It's a systematic way to solve the linear ODE. Last week we have started the process to study linear equation like this, and we use the simple harmonic motion and damp oscillation and force oscillation as our example to start the discussion. But the method I use is the so-called method zero. Method zero means it's so intuitive. And actually it's ad hoc. ad hoc is a very good word. It's very, very ad hoc. Ad hoc, do I pronounce it right? Ad hoc.
I don't know.
Ad hoc means it's not systematic. Okay, you do the things, you deal with your problem case by case. Okay, when you see the problem and then you deal with it whenever comes to your mind. This kind of thinking, this way is called ad hoc. It's called ad hoc, like Trump. So it's called ad hoc. Okay, so you can see that in our discussion last week. Actually, it's pretty ad hoc. It's not systematic. You may ask, is there a systematic way to solve this kind of linear equation? The answer is yes. Okay. So that's what I'm going to tell you. And actually, the method is very, very simple, except that you have to familiar with yourself with a little bit complex analysis. Okay, I'll tell you which textbook to go to, but you have to learn a little bit about complex analysis, then you have a systematic way to solve this kind of linear ordinary equation. So it's a very, very powerful way. It's a very powerful method. However, I started with an ad hoc method with a purpose, because I want you to first familiar with yourself with the physics content. Okay, it's the oscillation, it's the force oscillation that we are concerned with. 我们想要了解的是像这一类的 physics problem. Okay, and from last week, I hope you more or less understand the physics content, the physics context we are working with. 什么样到底在讨论什么样子的物理问题？ I hope I told you earlier that I want this course to be mathematical physics instead of physics mathematics. Okay, so it's physics that's the priority. Okay, however, so this ad hoc way to doing things, intuitive, improvising, may not be very, very systematic. However, it actually in the process. Actually, we have some very, very important theorems that could be applied in the long term. For example, we prove that if you have two solutions of the linear equation, for example, y1 and y2, both of them satisfy the linear equation. This is the linear ODE. y1, y2 is two of the solution. Then you can form a linear combination, which is C1 y1 plus C2 y2. This function will also be a solution of the original linear ordinary equation. The proof is downstairs, or maybe it's right here. But this theorem will appear so many times. You don't have time to prove it, okay, in your future study. So it has to be in your brain right away. This is a very, very important equation, very, very important theorem, okay? And actually, it does not only apply to the linear equation of the second order. It actually applies to linear equation of arbitrary order. You can prove it yourself. However, I think this example is good enough that you can understand this linear combination theorem. Okay, so that's the first theorem we found, and which will be very, very useful. And also, we have found that when we study force oscillation, I emphasize it is actually an inhomogeneous version of ODE. Inhomogeneous means there is a right-hand side which is not a derivative of the function or the function itself. Okay, it's an external source determined by outside source, outside force or outside whatever, okay, agent. So in terms of mathematics, it's a term which does not depend on y, the function, but only depend on the variable, okay? So the force exerted on the oscillation is a very simple example, okay? This kind of ODE, we call it inhomogeneous linear ordinary equation, And we prove, because we are going to prove what we got this week again, so I don't want to go back, but just mention the theorem we got you still remember the theorem? We say that the solution of an inhomogeneous ordinary differential equation can always equals to one solution of the inhomogeneous version plus the solution of a homogeneous version. Okay, yeah, again, the proof is here, okay, and the proof is here. And this is very powerful, okay? Powerful in terms of it can be applied to arbitrary linear ordinary equation to arbitrary order first. Secondly, in terms of writing a solution in terms of XR and XS, again, XR is the inhomogeneous solution. This is the homogeneous solution. We are able to put in the initial condition as long as we get an XR. XR is just the one solution, but whatever way you get it, 你用任何的手段 with whatever method you get one solution, then you can always add a solution for homogeneous. And in this case, the homogeneous corresponding equation is the damped oscillation. This is homogeneous, inhomogeneous forced oscillation, but the corresponding, if you get rid of the right-hand side source term, you get this equation, okay? So this is the corresponding, we say is the corresponding homogeneous version, 对应的一个其次的方程式 ，OK？ 好，当然你要记得我们要解的是这个，但是我们竟然知道说，你只要得到了一个这个方程式的解，你可以永远加上一个它的解给它，那都还是解，这样懂我意思吗 ？OK， 好，这个是一个 quite a surprise. The first time I learned this theorem, I was quite surprised that it is true. And if it is so, then it is easy to put in initial condition, because XR is just one solution. There is no freedom. There is no way you can put in initial condition. However, XS, the solution for the homogeneous one, usually has unspecified constants. And that's unspecified constants I can adjust for us to fit the initial condition. Usually there are two of them. Now there are two unspecified constants. For example, let me write down here. So here XS has a XM plus 5. The notation may be very complicated, but you better remember which one is specified, which one is unspecified. For example, M, for example, B, they are, of course, specified, right? B is the coefficient of the damping. M is the mass. They are given by the problem, by the question. However, Xm, the amplitude of the oscillation, phi, the phase constant, they are both unspecified. They could be arbitrary. They could be anything. Okay, that's what I mean by unspecified constants. Okay. And in the one solution we got, we call it resonance solution. We don't have that kind of freedom. Almost everything in the formula are specified. Even this phi, sorry, I use the same notation, but this phi actually is the phase that has been determined. Okay, you will see today, again, meet this phi. The point is, everything inside this XR, this resonance solution, this one solution, are all determined. There is no freedom to adjust anything. However, in the solution for homogeneous version, we at least have two unspecified constants. And therefore, we can specify, we can adjust. Adjust means we can choose Xm to be this number, phi to be this number, so that the initial conditions are met. Do you see that? Let me put in Chinese. 我们就可以选择这个 Xm 跟这个 phi 刚好就在那个值上面，好，它刚好让你的解满足起始条件。那 of course the formula will be very complicated. 好 when you determine Xm and determine phi. However, in principle you can do that because there are two equations, there are two unknown, unspecified constant. So two unknown, two equations, everything is determined. Do you see that? Okay, so if you put in the initial condition, and these are fixed. So we get one solution. This solution satisfies the ODE, and also the initial condition simultaneously. And there's a very powerful theorem in mathematics department that stated that there's only one solution that could do both. There's a theorem. I think it's called fundamental theorem of differential equation or something like that. OK， 在数学系呢有一个定理就叫做微分方程式基本定理。它说只有一个方程式可以同时满足 ODE and the initial condition。如果只有一个 ，you got it already 。You no longer need to find. OK, do you see my point? OK, so even though this method, this very ad hoc way to do things, we started with guessing one solution, by guessing. There are some motivation, but there's not really rigorous derivation. It's a very, very ad hoc way of doing things. However, when I got to this point, the one solution I have, when I add the solution from homogeneous version, and the two of them together satisfy ODE, satisfy initial condition, and the theorem, fundamental theorem, guarantee there's only one. So this will be the one. So this final step is so important. It guarantees that the solution you got ad hoc, improvising, is actually the one that is correct. 所以最后这一步其实很重要，要不然你之前用猜的，你怎么知道你猜的跟别人猜的会不会一样？答案是数学家告诉你，它一定要一样才行，不一样那就是数学出错了。OK， 不可能不一样，大家懂我的意思吗？好，那 even better, let me remind you that even better, now even though we need two solutions to give you a general solution of an inhomogeneous, however, the solution for the homogeneous version, the XS, actually does not matter at all because it is a decaying function. So whenever time progresses to infinity, then this term, the first XS, will actually disappear. Okay, so only the XR, the one solution we guess ad hocly, will survive. Okay, will survive. So I write it as X will go to XR with XS decaying away. Okay, decaying away. So last week I say that the initial condition does not matter. That does not matter because over time, the trace of any initial condition, any trace of the initial condition will disappear from your solution. Okay. Any questions? This is a very, very short recap of what we have last week. Today, we are going to go to the general solution. The general solution. I have some picture. I'll do that next week. I'll do that next week. Some picture, very interesting stories. Let's do it next week. Okay. So, what I'm going to present is how to systematically solve ordinary differential equation with constant coefficient. Okay, with constant coefficient. Actually, it can apply to any ordinary equation of any arbitrary order. Okay, even though the example we talk about is of the second order, but actually, when I first introduce the method, I will use the second order ODE as our example. However, the method could be easily generalized to arbitrary order linear order equation. The only requirement is that the coefficient must be constant. Okay, so this is an. That means this an does not depend on the variable. Usually, the linear equation could allow this coefficient to be a function of x. Remember, in the earlier transparency, this is fq or fx or whatever is a function of the variable x. But however, if we restrict our attention to these kind of equation with constant coefficients, then this systematic way could apply. Okay, this systematic way could not apply to a general case, but could be applied to all the ordinary equation with constant coefficients to arbitrary order. Okay, you can consult our textbook often at 7.3. Oh, at 7.3. I personally recommend the Feynman lectures. Feynman lecture. If you are not familiar with complex analysis, the complex analysis is dealt with very carefully from the starting point in this lecture, chapter 23, volume 1. See, resonance. Okay, the Feynman is talking about the same topic in this lecture, in this chapter. See, 23.1, complex number and harmonic motion. Okay, so if you are not familiar with complex number, go to this book. Feynman will tell you the detail from the beginning. Do not assume that you understand complex number at all. Okay， 在美国大学生没有学过复变，好，所以呢，老师在教的时候要从头教起，好，要从头教起，就是因为这个样子。好，所以 this chapter, I think also 21 and 22 deal with the complex number and harmonic motion. So you can go to the Feynman lectures, the volume 1, to have a deeper and slower starting of the complex analysis. And but if you are already familiar with complex analysis, that is the complex number, then you can actually go to this website of Professor Schwartz of Harvard University. When he taught wave for sophomore, this is an introductory course for sophomore. In lecture 2 and also lecture 1, he dealt with oscillator and linearity. Driven oscillator. Driven oscillator means forced oscillation. Okay, so this is one of the lecture. He actually leave very detailed lecture notes. Of course, a little bit shorter. So this is one of the example. Here you can see that x dt squared x dt x. This is the forced oscillation equation of motion. Okay, so this will be very, and not just 10 pages, only 10 pages. So if you want detailed discussion, go to Feynman. If you want an abbreviated but very succinct discussion, you can go to Schwartz. Okay, I can go to Schwartz. I think I put Schwartz in my website already. There you go. Here, highly recommended. You can lecture notes 1, lecture notes 2. You can consult these lecture notes for discussion of the okay. So simple harmonic motion. Okay, simple harmonic oscillator. Only 10 pages, 11 pages for the first lecture, and 10 pages for the second lecture. For the second lecture, very, very, very useful, very insightful. Okay, so now let's start. Now we want a general strategy to deal with homogeneous ODE. Let's start with homogeneous. Inhomogeneous will come on very soon. Let's start with homogeneous ODE with constant coefficients. Okay, and we have talked. We have discussed several of these kind of examples. For example, the decay, the simple harmonic motion, the damped oscillation, etc. And they all fall into this form: an dnx dtn sum over as a polynomial equal to 0. Okay, equal to 0. And we want a general strategy to deal with this kind of ODE. And remember, the solution we have arrived at in decay and simple harmonic motion include trigonomic, the 三角函数, trigonometric functions and exponential functions. OK， 好，在我们的解里面，同时有三角函数，同时有对数函数。So if we want the general solution, we probably will want a way to unify the trig function and exponential function. Yeah， 因为我们已经碰到了三角函数啊，我们也碰到了指数函数啊，所以你如果要有一个一般的普遍的一个解法的话 ，you better have some way to unify the trig function and the exponential function. Well, at first sight, it doesn't seem to be easy because trig function is oscillating. Exponential function is either decreasing and increasing, or increasing or decreasing. So they are so different. So at first sight, you will say, how could two different kind of function which behave so differently be united into a single approach? But however, the answer is yes. Actually, we can find a way to unify the trig function and exponential function. Let me show you. You simply look at the exponential function and take two derivatives of b exponential b theta over theta squared. And you already know then you will get b squared exponential b theta. That's how the exponential function will behave with respect to the second order derivative, right? And if it's a trig function, for example, that takes a sine function as an example, then the sine function, when we take a second derivative, it will be equal to minus sine theta. So on the surface, actually, at least in terms of second derivative, the two functions are so similar, right? Because the second derivative is proportional to itself times a constant. This constant is minus 1. Therefore, if we take this b equal to the square root of minus 1, then why don't we just assume that sine theta is equal to exponential to the I theta? That's the first thought. Okay. If you do this, if you assign this sine theta as exponential to the I theta, then the two will be the same. It is both a trig function and an exponential function. The key is that you have to allow the imaginary variable. 你要能够容许它的变数是一个虚数。No, this is not right. 这不对。It works for second derivative, but it does not work for first derivative. 当然啦 okay, of course. If you take first derivative, I skip the first derivative because I want to hide this embarrassment. But if you take a look at the first derivative, then e to the I theta, when you take first derivative, it is equal to I times exponential the I theta. Again, proportional to itself, but multiplied by square root of 1 minus 1. And if you take the first derivative of a trig function, sine theta over d theta, it is cosine function. Sine becomes cosine, so it's not the same behavior with respect to first derivative. Do you see my point? So this designation will work for second derivative, but it will not work for first derivative. But you see, when exponential I theta, e to the I theta, if this expression makes any sense, what it does when you take the first derivative is to multiply it by a constant I. When a number is multiplied by a constant I, so that means this exponential e to the I theta must be complex number. Complex number means it has to have a real part and a imaginary part. Oh, okay. So if this e to the I theta does have any sense, I haven't shown you any sense yet, but if this expression has any sense, it better has an imaginary part and a real part. For example, a plus ib. And then you see that when you multiply by I times A plus IB equals minus B plus IA. Oh, so multiplication by square root of minus 1 means you exchange the imaginary part and the real part. Got my point? Because here, when A plus IB times I, now the imaginary part becomes A, which is the original real part. Now the real part is minus B, which is originally the imaginary part. So exchange the real part and the imaginary part. Keep this in your mind. How about trig function? For trig function, if you take derivative, this should be theta, sorry. If you take first derivative, cosine theta becomes minus sine theta. Sine theta, when you take the first derivative, it becomes cosine theta. So the derivative of trig function will exchange cosine and sine. 它会把余弦函数跟正弦函数把它换过来。Oh, so if the first derivative of e to the I theta will exchange real part and imaginary part, and the trig function will exchange the sine and cosine, why don't I just assume that the real part exponential I theta is sine and the imaginary part of exponential I theta is cosine? 对，讲太快了。Why don't we just assume that the real part of e to the I theta is cosine function, and the imaginary part of e to the I theta is the sine function? Then, when I take first derivative, then I change the two, because the first derivative will multiply it by I. And I explained already, when you multiply a function by I, means you exchange the real and imaginary. And the sine function and the trig function, when you do first derivative, you exchange cosine and sine. So I would suggest, not me, but Gauss in 1800 suggests we can identify the real part with cosine, the imaginary part with sine. Ladies and gentlemen, the first formula of Gauss. Okay, first introduced by Gauss, exponential to the I theta. Exponential to the I theta. Wow, it's an art. It's an art. 这是个艺术啊。Okay, there is no exponential to the I theta in nature. 在自然界有什么东西叫 exponential I theta？ 没有这回事啊。So it's a creation by mathematician. It's a creation by mathematician. There is no exponential I theta in nature. Of course, we have exponential function in nature, but that's real function. So everything in the real world is real. So if you say, I want an exponential function of an imaginary variable, actually you are creating something in your mind instead of nature. But it's such a beautiful creation, and so beautiful and so useful when we apply it to mathematics and physics. You will see this is very, very natural choice. OK， 好，你就会发现这样子的一个选择呢，事实上非常非常非常的自然。OK， 好 ，Ladies and gentlemen, the formula invented by Gauss or written down by Gauss, exponential e to the I theta is equal to cosine theta plus I sin theta. Now I can check when I do the derivative. I can check what I said is true again. When exponential I theta, I take the first derivative d theta, and it is equal to I times exponential I theta. Okay, so that means you multiply the whole thing by I, then this becomes minus 1. And the imaginary part now becomes the real part. And then the original real part multiplied by I now becomes the imaginary part. So exponential I theta over d theta will be equal to this. And you can also do this by applying the derivative directly on the real part and imaginary part. So cosine theta, when you do first derivative, it becomes minus sine theta, of course. And sine theta, when you do first derivative, it becomes cosine theta. So the two approaches are consistent. You can directly take derivative from here to here, from here to here. You can also take the derivative by taking this I down, and the first derivative exponential I theta equal to I times exponential I theta. Okay. We can do it again. If you take the derivative twice, then this will become minus cosine theta, because the derivative of sine theta is cosine theta. And cosine theta, the derivative is minus sine theta. Let me check if it is equal to I squared e to the I theta. Of course, it's correct, because I squared is minus 1. So it is minus exponential I theta. So if e to the I theta is this, then this term becomes this. And therefore, they are consistent. Okay. So you can approach it by trig, you can approach it by exponential, but the two approaches are consistent with each other. Okay. Any question? So that means this definition is consistent with respect to differentiation. However, there are some other, so that means we can prove very easily if the constant, if there is a coefficient in front of the imaginary variable. For example, instead of e to the I theta, we now have exponential e to the I alpha x. Alpha is a real number. Then if you take the derivative to the nth order, it is very easy to prove from what we have here. The result will be I alpha to the nth times exponential I alpha k x. Okay. So this is exactly what we would expect from ordinary exponential equation. 所以这个结果就跟我们希望的一般的指数函数的结果是一模一样的。好，这个指数如果是指数函数的话呢，会预期 x e to the bx 你会预期把一个指数函数做 n 次微分了以后，就等于 b 的 n 次方乘上这个指数函数本身嘛 ？For real exponential function. Okay, so now I extend this formula for real exponential function to exponential function with imaginary variable. Okay, 好，虚数指数的函数也满足一模一样的规则。Not only this, I can also check another very famous formula that is true for exponential function. That is, if we, for real function, if you multiply two exponential function, e to the alpha times e to the beta, and I think the high school's mathematics teacher must prove to you already it is equal to exponential alpha plus beta, correct? So now I'm going to prove this is also true with this new definition. Okay, so it's important because this is a very useful and we apply so often when we start to exponential function. So now I check exponential e to the I alpha times e to the I beta, whether it will be equal to e to the I alpha beta. That's my purpose. But it's very easy to check. E to the I alpha equals to this. E to the I beta equals to this. If you multiply the two with each other, then it is easily expanded into this form. And the real part consists of cosine alpha, cosine beta, minus sine alpha, sine beta. That's the real part. Plus, the imaginary part is the cross term, sine alpha cosine beta here. Cosine alpha, sine beta is here. Imaginary part. This is the real part. And those of you who are familiar with the formula for trig function can easily identify this as cosine alpha plus beta. And this is sine alpha plus beta. If you don't understand this formula, you can go check with any, ask ChatGPT how to prove it for you. So this is cosine alpha plus beta plus I sine alpha plus beta. And of course, according to definition, it is e to the I alpha plus beta. QED, so it's proven. So that means for our exponential function with imaginary variables, they satisfy the same formula as real function, real exponential function. Okay, so everything you remember about exponential function can be applied to the new form directly. That's the key of the definition actually. Gauss have checked all the rules about exponential function applied to the new definition. 所以高斯当年就一个一个的 check 过了，所有跟指数函数有关的这些规则，微分也好，乘积也好，点，在这一个新的定义底下都是成立的，都是成立的，这个没问题。Okay. So if you understand this page, then our test will be very easy because it could be applied directly to the solution of a linear ODE. Okay, let's be not that fast. There's another derivation. Those who are familiar with mathematics and calculus will know that there is actually a Taylor expansion of the trig function. For example, cosine theta could be expanded as an infinite series. Sine function could also be expanded by Taylor expansion as an infinite series like this. And the exponential function also has a Taylor expansion. So if you put in x equal to I theta, plug in x equal to I theta, and simplify it, you will see that the real part indeed is equal to cosine theta. And the imaginary part equal to sine theta. Of course, this is not a proof. This assumes that the Taylor expansion also apply to the new definition. Okay, but it is easy to remember, it's easy to remember if you are familiar with these two infinite series of trig function. Then you can just plug in I theta. Then you got the correct result. Okay. Now, any question? So I have explained everything about the exponential function with imaginary variable. Now I'm going to extend it into exponential function with complex variable. Complex variable means now instead of I theta, now I have an alpha, a complex number alpha in 在这个 exponential function, inside the exponential function, e to the alpha. And this alpha is a complex number, so it has a real part a, and an imaginary part, I call it theta. So e to the alpha, I define, this is of course a definition, okay? I define it as exponential a plus I theta. And if I assume that all the rules apply, all the rules about exponential function apply, then this could be separated into exponential e to the a times e to the I theta. Then if you do this separation, everything is clear. Because e to the a is just a real number. And e to the I theta is just the definition I have shown you earlier. Cosine theta plus I sine theta. Okay? So this e to the alpha has a very simple explanation in the complex number space. 复数平面，高中是不是教过复数平面？有没有？有 OK 好。So if you are not familiar with complex numbers plane, so-called 复数平面, go to Feynman. Feynman lecture will explain. But anyway, it's not that difficult. You just plot the real part of a complex number on the x-axis and plot the imaginary part of this number on the y-axis. So every point, every complex number corresponds to a point. Or in reverse, every point corresponds to a complex number. Okay, so this is definition actually give you an idea that the system of complex number are actually a two-dimensional system geometrically. Okay, but we'll wait to talk about that later. And then, for example, this e to the alpha is this point. Assume that it is this point. Then it is easy to identify this number with the diagram. The real part will be e to the a cosine theta, and the imaginary part will be e to the a sine theta. Okay, so it doesn't take an explanation to understand that. That means the length of this vector is equal to e to the a. And this angle is just the theta. Is that clear? It's very important, so you have to understand. Okay, for this number, e to the alpha, the length is e to the a, the real part. And theta corresponds to this angle. It's easy to identify, right? And there are some definition and terminology about these two properties. The theta is called argument, 中文叫做辅角. And e to the a is called the absolute value of this complex number. Okay, so the notation is this. So it's called absolute value. And in terms of the diagram, the absolute value is just the length of the vector representing this point. Okay. Then, therefore, with this definition, then it is easy to prove some very, very helpful and very, very useful formula. For example, the absolute value of e to the I theta is equal to 1. It's so simple, I just stated it is true. Okay, I will just state it is true. If you have any doubt, you can prove it yourself or come to me. I will show you on the blackboard. So exponential I theta is equal to 1. Okay, because it is equal to cosine theta plus I sine theta. Oh, sorry, I should have write the definition of absolute value. For those of you who do not know complex analysis before. So if it's a plus ib, the absolute value is defined as a squared plus b squared, the square root of it. Okay. So it is easy to see the definition equals to the length of the vector, right? Because a, the complex, the real part, b, the imaginary part. So a squared plus b squared, take a square root, is equal to the length of the vector. Okay, so that's one of the definition of the absolute value. And if you apply this definition to the e to the I theta, then it is easy to see that cosine squared plus sine squared is equal to 1. Taking a square root, it is equal to 1 also. Okay, so e to the I theta equal to 1, very easy. And then e to the alpha, if you take the absolute value, as I say, it is e to the a, so you can do this. Okay, and I claim that any vector, any complex number can be expressed in this way. It is equal to the absolute value times exponential I theta. Okay, it's easy to prove, but please understand this claim. Yep.
So I theta is always equal to 0.
What?
I theta.
I theta is always equal to 0. No?
Yeah,
Why?
No, I just make sure.
No. I think theta is this angle.
Yeah, but it always is 0, right?
What is 0?
I theta. No.
I theta. No, it's an angle.
But why e in the power of I theta equals to 1?
e to the I theta absolute value equal to 1.
Yeah. So
It does not mean I theta equal to 0. No.
why?
Why? Okay. Let me turn on the light and show you. This is very important. Thank you for asking. Do you see this definition? Okay. So definition, the absolute value of a plus ib is equal to a squared plus b squared square root. So what I want to do, and you ask, is e to the I theta, the absolute value, right? Then e to the I theta is cosine theta plus I sine theta. So according to the definition, you just plug in the definition, it is equal to cosine square theta plus sine square theta. Take the square root, and it is equal to 1. Okay, thank you. Yeah, that's a very good question. Okay, you have to understand this, otherwise you cannot go ahead. So, yeah, of course, if theta is 0, then it is equal to 1, but it does not mean that theta has always to be equal to 1. Yeah. Very good. Yep.
Why we define alpha as a? Oh, okay. 看错了。
Yeah, this is A, this is alpha. Yeah, sorry, it's hard to see on the backboard. 等一下，我先把灯关一下。所以我才说你要回家看一下投影片，因为在黑板上哈，alpha 跟 A 非常容易 confused。Okay, here is alpha is a complex number. Alpha 是复数，这个复数呢是等于 A 加上 I theta。那 A 是一个实数 ，theta 是一个实数。慢慢来 ，OK， 好，那所以呢，这一个 e to the alpha， 我就可以定义它是 e 的 a 乘上 e 的 I theta， 因为很自然嘛，好，根据我们所熟悉的这个指数函数的这个运作规则，那这件事情呢会是对的。那当这件事情会是对的的时候，我可以把这个 e 的 a 提出来 ，e 的 I theta 就直接写成 cosine theta 加上 I sin theta， 因此。这个 e to the alpha 的实数部 ，e to the alpha 的虚数部，就全部知道啦。好，就全部知道啦。OK， 你自己读啊，就是 e 的 a 次方乘上 cos θ，e 的 a 次方乘上 sin θ。那你如果把它画在这个复数平面上面，就看得更加清楚了。因为 e 的 a 次方 cos θ 就是它的实数部，就是它的 x 轴坐标分量。那e 的 a 次方 sin θ 就是它的 y 的分量 ，OK， 好，就是它的 y 分量。所以呢，我们常常就把这个 θ 呢就叫做这个幅角，而 e 的 a 次方就叫做它的 absolute value， 也就是这一个 vector 它的这个长度。好，所以这一页 this page is very important for you to understand every detail of the complex analysis, the preliminary complex analysis. Okay. As an exercise, you can go back to proof. If I have two complex number m times n, and I take absolute value, then it will be equal to m absolute value times n absolute value. It's so easy. I usually don't prove until yesterday. I think about it. Is it easy or is it hard? But before I prove it, this is simple, so remember it. Print on your brain, this is true. Okay, we'll use it very often. Again, when there are two complex numbers, we take the product and the absolute value is equal to, we take the absolute value respectively and take a product. 它好不好证？它很好证啊。It's very easy to prove. Let me show you in this blackboard quickly. Give you a hint. If m and n, I write it as m. I express it in terms of this way, and I call m equal to what's the notation? M factorial. 它的这个 absolute value times I theta 1. Let's call its angle theta 1. And n, the absolute value times I theta 2. This theta 2 is the argument of 俯角 or angle of this complex number. Theta 1 is for m. And then if you multiply the two together, then you got m times n equal to m factorial, oh no, m absolute value times e to the I theta 1 times n times exponential I theta 2. To this point, you all know the answer already. Because now I have 1 factor, 2 factor, 3 factor, 4 factor taking multiplication. But you can switch the order. You can simply switch the order. So it is equal to m absolute value times n absolute value times this, and we can combine them into I theta 1 plus theta 2. We are almost done. If I express in this way, and I take the absolute value of the product mn, then this is a number. This is a number, right? So when you take the absolute value, only this needs to be taken absolute value, because only this one is a complex number. But we know already all the exponential function to the I theta equal to 1. So the absolute value of this guy is equal to 1. So we are done. So the absolute value of this equal to absolute value of m times absolute value of n. Very simple proof. If you can utilize all the very various facts about the complex number, then this kind of proof is very easy. 可以吗？好，回去想想看，好，稍微想一下。Now, with this definition, we can go ahead to prove that a very, very important expression, a formula, that is, if I take the derivative of complex variable exponential e to the alpha x, 这个如果我要把它对 x 做微分的话，把它对 x 做微分的话 what I need to do is to separate this alpha x into ax plus I theta x, 可以吗？Then when I take derivative, I can use chain rule to take the derivative of the first term first and the second term second. And then the derivative of the first term give you an a. The derivative of the second term give you a factor of I theta. When you combine the two together, it becomes a plus I theta times e to the a plus I theta. Remember, a plus I theta is just alpha, right? Eventually, I got e to the I alpha x, take a derivative, is equal to alpha times e to the alpha x. Oh, 早讲嘛. It's so simple a formula, but it takes a proof to prove it is true. Okay, that is the same as this one. The real case. Every time you take a derivative of exponential, you multiply it by a coefficient. And 2 pages before, we proved the same kind of formula for imaginary variable exponential. Now, I prove it again for complex number, complex variable exponential. So this is final. This is final. If you want to remember something, remember this. Exponential alpha x derivative equal to alpha times the exponential alpha x. It's so similar to what we have in real physics. That's the real power of this definition, because we keep all the rules of ordinary exponential function to exponential function of complex variable. 我们把所有的旧的规则全部都适用在这个新的定义上面，这就是它的最厉害的一个地方。我们竟然可以找到这样的定义，把所有的旧规则都可以放上去。Okay, now so I see that. Let me put it in English. The derivative of a complex exponential. Complex exponential, I mean this e to the alpha x. Exponential function of complex variable equals to the coefficient times the exponential. Okay, so this is only for first derivative but the same thing could be applied several times, and you can easily convince yourself e to the alpha x taking the derivative to the nth order will be equal to alpha, the coefficient, to the nth order times exponential alpha x. So the derivative of nth order equals to the coefficient to the nth power times the exponential. Okay, so this is the most important formula we come to at this section. Okay, let me summarize. So that's the end of our definition of e to the alpha x. Therefore, our starting point is to ask you, is there any way to unify the trig function and the exponential function? Now I give you one. That is the exponential function of complex variable, like e to the alpha x. It is easy to convince yourself if this alpha is real. If this alpha is real, theta is equal to 0, then it's just an exponential function. If the alpha is imaginary, that means a is equal to 0, but theta is non-zero, and then it becomes a cosine function, and the sine function is oscillating. Okay, if the alpha is both, by both I mean it's complex, has a real part and the imaginary part, then e to the alpha x is the product of a trig function and an exponential function. That's the conclusion of our first section. Is that okay with you? Is that okay with you? Very simple. Remember, please remember it. Okay. So even better, the differentiation of e to the alpha x follow very simple rule, as I have shown you already. Follow the same rule as the original real exponential function. That is, again, the nth order derivative of e to the alpha x equals the coefficient alpha to the nth order times e to the alpha x. Now, I'm going to apply this rule to solve simple harmonic motion. And then we'll take a break and come back, and we'll use the same procedure to damp oscillation and to force oscillation. And we are done. You can go. Now, let's do the simple harmonic motion by complex number method. Of course, there is no complex number in nature. So everything in this equation, dx squared dt squared plus omega squared x are all real. But could I pretend it's complex number? That's the first step of thought. Could I pretend that this x is actually a complex number z? I give it a different name to remind you that it is now I extended, elevated, whatever you call it. This I pretend this becomes a complex number, z. So this equation is elevated into a complex ODE, d squared z over dt squared plus omega squared z equal to 0. You say, well, come on, I'm talking, the teacher gave me the homework, and he said it's a real equation. But if I solve this equation, could I get back to the original one? The answer is yes. Because this z is a complex number, a complex function, therefore it has a real part and an imaginary part. I'll use this notation. Re means z, real part. Im, z, means imaginary part of z. So this z could be written as real z plus I image z. Is that okay? We just plug in the notation. It's the same thing. Same here. Plus 0, but 0 is 0 plus I0. Oh, why do I write it this way? Then I can separate the whole thing into real part and imaginary part. And the real part of z only contribute to the real part of the equation. Imaginary part of z only contribute to the imaginary part of the equation. So this guy, this equation, because the equation is linear, so I can easily separate this term into this plus this. And this term is easily separated into this plus this. And then if I separate the real part and the imaginary part, don't remember when a complex number is equal to 0, it's not just one equation. When the complex number equal to 0, that means the real part is 0. Also, the imaginary part is 0. Okay, so the real part is equal to 0. Boom. The imaginary part has to be equal to 0 also. So that shows you the real part of z and the imaginary part of z both satisfy the same equation of most differential equation. And remember, REZ is real, IMZ is real. 这里写虚数部，但你不要忘记虚数部就是实的啊。It contributes to the imaginary part, but itself is real. So got a two solution to the original equation, right? Got it? So since the equation is linear, so both the real and imaginary part will satisfy the original real equation. So if we can solve complex z, its real part and the imaginary part will be the solution x of the real equation. Let me put it in Chinese. 我们把它从实数的方程式升级成复数的方程式，照理讲变得比较麻烦。但是我们很确定的是，如果我们的这个 z 呢可以解得出来的话，它的实数部、它的虚数部都满足原来的方程式。这句话可以接受吗？这一定要能接受，不然我们讲不下去了。OK， 好，那你当然你的问题就是，我解这个方程式比较简单，还是解那个方程式比较简单啊？The quick answer is, it is easier to solve the complex version than the original version. 简单的答案，算这个复数的这个版本，远比算一个实数的版本要简单得多。你相不相信 ？Let me show you. Now, the complex version, z t squared plus omega squared times z equal to 0. Let me guess. The answer is z0, a complex number constant times exponential alpha t. This exponential alpha t is just similar to what we have here, exponential alpha x, but now I choose the variable to be time, okay? Now, I guess this will be the answer. See what happened. If I plug in this answer to the equation, the point is, all the derivative is proportional to z. Yeah, I showed you already. The e to the alpha t, every derivative of it is proportional to itself, and the coefficient to the nth power. So z over dt to the nth is equal to alpha to the nth power times z. 有没有问题? If I assume that z is like that, it's a complex variable exponential function, then I'm sure this formula will apply. Then if this formula will apply, the second derivative is equivalent to alpha squared. And then there is no derivative, so just alpha squared z. Ladies and gentlemen, the original differential equation now becomes a algebraic equation. 原来是一个微分方程式，经过这样子的变身了以后，它就变成了是一个代数方程式。从大学回到了高中啊，大家懂我意思吗？大学学微分方程式，高中学代数方程式，我们从大学回到了高中啊。That's the key. That's the key. This kind of thing could not be done for real ODE. But it could easily be done for complex ODE. So we make the thing complicated, but make the thing easier. Okay, now it's easy to say that this alpha squared plus omega squared is equal to 0. Okay, we just take away the z from both sides, and alpha squared equal to omega squared. Alpha is still unknown. Omega is the parameter of the simple harmonic oscillator. So we got two solutions. Alpha could be positive I omega, could be negative I omega. Okay, so we got two solutions. Complex solution. These two complex solutions, z0 exponential plus minus I omega t. Ladies and gentlemen, the complex form of oscillation function. You will see this kind of function again and again and again and again in the 4 years of your college life because it appears in almost every branch of physics. 它在物理里面几乎每一个部门都会出现这样的解。Sometimes the textbook or the teacher will not tell you that actually we are talking about the complex version, not the original one. The original one is a real function, a real equation. Sometimes the textbook, because it's so simple and it's so straightforward, so sometimes the teacher or the textbook will forget to tell you that it is actually what we're working at is actually the elevated version, the complex number version. Okay, so you have to know yourself. Okay, whenever you see this kind of solution, when teacher or textbook states that, let's assume the solution look like this, you have to remember, it's not the solution of the original equation, but the extended or elevated complex version. 真的，老师有的时候忘记讲，教科书有时候忘记讲，直接就告诉你说，让我们假设它的解长得像这样 exponential plus minus I omega t. So you better remember this form. You better remember this form. Okay. 好， you say, wow, exponential plus or minus I omega t. Is this the oscillating simple harmonic motion we are so familiar with? Yes, the answer is yes. Now, let's get back to the real world. Here again, this is a complex solution. It's a solution with complex number. But remember, we are living in the real world. So we have to remember our original assumption is that when we solve z, then we take the real part and we get a real solution. So now let's get the real part of z plus, real part of z plus. Here, I will assume that this z0, the constant, could be written as a times e to the I alpha. Okay, this z is just a constant, but it's a complex constant. OK， 以前叫做 c， c 因为是实数嘛，对不对？可是这个 z0 is actually complex number. So if it is a complex number, it has a real part, has imaginary part. It is even better to express it in terms of the absolute value and the argument, the 辅角. So here I will express this z0 as a times exponential I alpha. Is that okay with everybody? I can do that, right? Okay, I can express the z0, and the a and phi are unspecified. But if you plug in this z0 to the solution, then the solution, remember the solution is z0 times exponential. Now we are talking about z plus, so it's exponential plus I omega t. So the solution combined together with z0, a times exponential I omega t plus phi. So take the real part. This is complex solution. So take the real part. It is a cosine omega t plus phi. Bingo. We come back to the solution we are so familiar with in general physics, in high school physics, the solution of simple harmonic motion. A times cosine omega t plus phi. This phi, the phase constant, A, the amplitude, is the absolute value of z0 and the argument of z0. Okay, so now I got the real solution. I got two unspecified constants, and we can use these two unspecified constants to fit initial condition, just as we have described last week, the week before that. And then the final function would be the unique solution to both satisfy the equation and initial condition. We are done. So we use a very powerful method to solve the simple harmonic motion problem. Okay, let's have a break. In the next half an hour, I'm going to extend this method to damped oscillation and forced oscillation. I can finish in 20 minutes, believe me or not, because I can copy all the pages to those new cases. And you will see, it is so systematic, you can apply and learn very soon. Okay, so let's have a 10 minutes break and come back.